This podcast, which is also part of Unit 1, is about measurement, uncertainty, and calculations in science, in chemistry. So first, talk a little bit about the scientific method, steps for the scientific method that we talked about in class. And these can be described a little bit differently depending on what book you use, but they should all have some things in common. Observation, followed by some sort of hypothesis, and then experiment and collect data, analyze the data in your experiment, and then come to some sort of conclusion. And then based on that conclusion, you can either revise your hypothesis or start from scratch. So we get this loop that happens here so that we actually are never really done with the scientific method. Things that we need to think about as we set up an experiment are controls, and those are variables that are held constant in a scientific experiment. And often error involves not being able to control the controls as well as we need to. Manipulated variables are purposeful changes, so things that we are changing on purpose, sometimes called the x-axis. In a graph, things that we are purposely changing. Independent variables. Responding variables are the data that you're going to record as the experiment happens, and these are the dependent variables, and they usually go on the y-axis. Experiments tend to generate numbers, numerical results. We measure things like mass and volume and pressure and temperature, time, and other things that are all numerical. And this leads to two types of error in measurement: systematic and random. Systematic error tends to be a function of the measuring device. If your device is not calibrated, let's say you were measuring time with a clock that was slow, that would lead to systematic error. All the errors would be in the same direction. Random errors, those are related to laboratory techniques, and those tend to be not all in the same direction. But with better and better technique, we can minimize random error, but they will never totally go away. Accuracy is how close your results are to the true value. So for example, if you're measuring the density of an object, and at the end of all your work, you look up the true density, how close did you come to where you're supposed to be? That is how accurate you are. Precision is a function of your measuring device. It measures how close the values are to each other. If you have a really good measuring device, they're going to be closer to each other, and therefore you're going to be more precise. Also, the number of decimal places, or the number of significant figures that you have in your value, that's also called precision. And that's also a function of your measuring device. So one way to think about accuracy and precision is with actual lab data. So looking at A, B, C, and D, which go in this kind of strange order, A, B, C, and then D, looking at these four graphs, figure out which one was precise but not accurate, which one was accurate but not precise, which one were both accurate and precise, and which was neither accurate nor precise. So go ahead and stop the video and try your best, and then turn it back on and see how you did. Okay, these are the results that we come up with. Precise but not accurate is B, and precise because these values are all really close to each other. They're all really close to 27, but they're not accurate because the dotted line down here at 25 is the true value, and they are all not very close to that. So they're not accurate, yet they are precise. This is a really good example of systematic error. Something's causing all of our measurements to be off by right around 2, and that's probably a function of calibration or something to do with our measuring device. Accurate but not precise is down here in C. So it's not precise because they're sort of all over the place. Some are up above 25, some are below 25. However, if you were to take the average of all of them, they would come out right near 25, so therefore they are considered accurate. Both accurate and precise would be here. Very close together, that's precise. Close to 25, that is accurate. And then for D, they are not precise because they're not close together, and because all of them are higher than where they should be, they're also not very accurate. So this is actually not where you want to be. What is measurement? Measurement is the data that you take. It's not a calculation. They're the actual numbers that you record during an experiment. Uncertainty is the estimated value in your measurement. The last digit reported in a measurement is always estimated, so that is our uncertainty. So when we look at the beaker here, this is in milliliters, so the beaker here starts at 20, and then we have a dashed line at 30, which isn't numbered because of space, but it's there, and then 40, 50, 60, 70, 80. So we have lines or hash marks at the tens place. Because we know that the volume is somewhere between 40 and 50, 40 is certain. We know that it's above 40. 50 is certain. We know that it's below 50. And we are going to estimate where it is in the middle. So we know it's between 40 and 50, and we can estimate 47. It might be that you estimated 48, and that would be okay. But this 7 here is the estimated value, and it's always the last digit. This is a burette, which means we have to read the numbers backwards. And it has a meniscus, which we read at the bottom right here. The bottom of the meniscus is the volume that we actually read, not up here on the side, so be careful with that. We know, because of the precision of our glassware, so this is 20, 21, 22, 23, and 24, we know, this is 20 and this is 21. So we have hash marks at the tenths place. 0.1, 0.2, 0.3, and 0.4. We know that it's between 20.3 and 20.4. That is for certain. We estimate that it's a little bit closer to 0.4 than 0.3, so 20.38. The 8 is our estimated value. Not everyone will pick the same estimated value, and that's totally fine. You might have said 23.7, 23.9. Those are all okay. These are the certain numbers. 20.3, last digit is estimated. But the device that we're using to measure determines the number of digits that our measurement is going to have. It's really important that it has the right number. Why does it matter? Isn't 2.00 the same thing as 2? And it is not. Because if we look at 2.00, this last zero that's in the hundredths place is the estimated value, which means to measure this, we use some really high quality, precise glassware. Over here, 2, no decimal, no zeros, is the only digit, so that is the estimated digit. So we know that the number 2, the value 2, is somewhere between 1 and 3. That's not very precise. So the number of digits that our measurement has is really important, and it shows what we use to measure it with. What's confusing about this is when you plug these numbers into a calculator, 2.00 does exactly the same as 2 in a calculation, so you have to do the thinking for the calculator. The calculator's not going to do it for you. Okay, significant digits or Sig Figs, significant figures. All of those mean exactly the same thing. What are they? They're the measured plus estimated numbers in a measurement. Rules for determining the number of Sig Figs in a number. All non-zeros are significant, and I will add that any zeros that are in between non-zeros are also significant. Placeholder zeros are not significant, and those include leading zeros that start out the number and ending zeros if there's no decimal. So there's a link in Schoology for a video that talks about where to round. That's a really good thing to look at. So go look at there, watch the video, and it'll help you remember what the rules are for where to round. So I don't get it. When are those zeros significant? Let's look at these two numbers. 0.001 kilograms. The leading zeros are not significant, so we have to have them, but they don't count for our sig figs. And 0.001 only has one sig fig. 2000, with no decimal. Because it has no decimal, these ending zeros are also not significant, so this number here only has one sig fig. This one's a little bit more complicated. The leading zeros are not significant, but the ending one is, because it comes after a decimal. It ends, and there is a decimal in the number. So this number has the 1 and the final 0, so it has two sig figs. Exact numbers are counted, they're not measured. And those, for exact numbers, we do not count the number of sig figs. So for example, if we said, we have a class with 23 students, I did not estimate that 3, I counted it exactly. Or 465 books, I counted them exactly, they're not estimated. I didn't use a measuring device to measure them. So when we have counted numbers, we ignore how many digits they have when we do calculations. So for practice, go through these and for each of the following, underline the zeros that are significant and determine the total number of sig figs in each quantity. Don't worry about the scientific notation, the exponential notation. We're going to do that later. Stop your video, try it on your own, and then start it up and see how you did. Okay, so check your answers and come and see me if you have any questions. Scientific notation is using exponents, power of 10, for very large and small numbers. So to convert back and forth between scientific notation, one of the nice things is that we only use sig figs in scientific notation. So it's a really good way to count sig figs if you're not sure. Take your number, put it into scientific notation. So practice putting these numbers into scientific notation. Stop your video, try it yourself, and then start it back up and see how you did. Okay, so just to show you how useful this is, 5.0 times 10 to the minus 4, because this 0 is a significant digit, we do use it when we convert to non-scientific notation. And when you put a number in scientific notation, you drop all of the placeholder zeros. So it's really easy to see that this number has only 3 sig figs, and all of these zeros are placeholders and not significant. To use a calculator with scientific notation, make sure that you know how to use the EE button or the EXP button or whatever function your calculator does. Do not use times 10 or a caret. If you're not sure how to do this, come and see me. It's really important. It's really important to keep track of the number of significant digits because calculations should reflect the precision of what you use to measure. You cannot make a measurement more precise by doing a calculation, so you can't add extra digits. Rules for significant figures or sig figs in calculation. For addition and subtraction, the rule is that we round to the smallest place value. So the 0.9 here is the smallest place value, so when we do the math, we have to round to that place. The rule for multiplication and division, which is much more common, is that we round to the lowest number of sig figs. So if we multiply these 3 numbers together, we first have to look at the sig figs. 3 sig figs, 2, and 4. But 2 is going to be the smallest number, so we're going to round to 2 sig figs. So after we do all the calculations, put everything into your calculator, look at your answer and say, okay, I've got to round to 2 sig figs. I'm going to round that to 19. Round 5 up. We don't use any fancy statistics for rounding. And if you have a multi-step calculation, put everything into your calculator, write everything down, more digits than you need, and then figure out where to round, because 0.8 0.85 has only 2 sig figs, my final answer cannot have more than 2 sig figs.